slope failures happen in Malaysia. For example, in the 2004, we had a slope failure which rock falls in Bukit Lanjan in the North-South Expressway. As you can see, these are major massive rock falls and it affected to the road damage. And the next figures on the right side here, it was happened in 1999, the landslide in the Bukit Antarabangsa, Hulu Klang. I think that these are two cases that very famous in Malaysia. If you Google, you might find out these are the two things failures happen in Malaysia: road fault and also the landslides. And the things or the factor that we have to investigate what are behind the story of the rock failures or the landslides happen. And the next one on the definitions. The slope stability is the potentials of naturally occurring or engineered slope soil, for example, embankments, cutting, open pit mining, excavations, landfill, to withstand ground movement. What does it mean here is that when we do any constructions or any slope constructions, we have to ensure that the slope, whether it is a natural slope or man-made slope, must be in a stable condition. How to ensure that the stability of the slope, the factors control to the stability of the slope, for example, here is the slope geometry, and also the what we call it is the shear strength of the soil itself. And then the instability of the slope may cause due to the seepage and the gravity forces. Okay, as you can see here, this is example a stable slope. There is no any movement, for example, rock falls, and then you can see that this is a very static conditions. What happens next is you can see the mass movement or the rock falls getting happening from one block to another one block. It means that by definition, the mass movement is caused by an increase in shear stress and decreases in the shear strength. So it says here that it is happening when the shear strength getting lower and it is taken by the shear stress. I believe that in the soil mechanics, you have understand the meaning of the shear stress and also the shear strength, and also how these things influence the strength of the soil. So whatever applications in geotechnics, it is relates back to the strength of the soil. Similar to the slope stability. As long as the shear strength are high or increased, we can ensure the stability of the slope. As again I said, there are many cases there are many factors involved in the slope stability or the mass movement. And then we go to the next type of slope. Okay, as you can see here, there are two types of the slope that we can define here. For example, natural slope and also the man-made or engineered slope. The natural slope, for example, here is the cut slope, built or deposited slope. And then for the man-made slope, for example, here, built slope and the cut slope. A simple thing is here is that if the slope in the original conditions, we can see that the slope in the natural types of the slope. And then when we do some constructions or near to the slope surface, it has been changed to the man-made slope where we have did some changes on the slope geometry. So this easier way to split or to differentiate the types of the slope, whether it is natural slope or the artificial slope. As you can see here, a lot of constructions has been done, constructed on the hillside and then on the valley, because of the environment close to the slope or to the hillside is very nice. So that we can see a lot of the constructions being done on the hill slope face, and then we can see that during the constructions, we may find or we may face slope failure. But then how we tackle the issue so that the slope failure might not take a lot of damage losses. So these are the things as a geotechnical engineer that you have to bear in mind when you are doing the slope constructions. What it says here, we understand the definitions of the slope, we understand the category of slope, and we have to take the precautions when dealing with the slope failure, for example, or the slope stability. And then when we go to the category under the built man-made slope, or the cut slope, these are the things that we might find from here. For example, embankment and dam slope, and then we have the cuttings and unsupported excavation slope. If you are doing the road constructions, these are also involved with a cut slope. And again, these are the images shows to you the difference between natural slope and the man-made slope. So you can see that the natural slope is very nice, and then there's a lot changes in to the slope face due to the weathering process. There's nothing involved with a man-made hand or by human actions. However, when you look at to the right side of the image, it is a man-made slope where this is the cut process involved, and we have to retain from the slope failure by using the gabion, or what we call it here is a retaining wall. This is the what we call it a method process to ensure slope from fail. So the easiest way when you go traveling along the North-South Expressway, we can see these two things are slopes. I mean that the natural slope and then the man-made slope. When you are reaching to the Manora Tunnel, you can see that there are some examples on the natural slope, which is the original our forest. There's some behind that can be a natural slope. However, when you go beyond that, you can see there's a lot of slope have been made or have been constructed just to allowing for road constructions, and how the maintenance or how the retaining wall or whatever used to ensure slope from fail. I think that's these are things you can observe from our life to take what we have learned in class and to adapt with the our life knowledge. And then when you categorize type of slope according to three mentions or three factors here, we can categorize type of slope according to the method of constructions, to the extent of the slope itself, and to the slope material. And when you look at to the method of construction, for example, here again we have found on the natural slope and also the man-made slopes. It means that does it involve with a method of construction? What kind of method of constructions? Is it involved with cutting and etc.? So that you have to identify from the natural slope, it can be changed to the man-made slopes. And then when look at to the extent category, for example, infinite slope or the finite slopes. Infinite slope, for example, you can check on the, if you are doing the what we call it, drainage per paritan. So some kinds of the slope we are in the infinite slopes. And somehow when you are doing with the some deep excavations, that's a finite slopes that involved during the constructions. And then the types of slope also can be categorized accordingly to the soil material. For example, cohesive soil and cohesionless soil. So we totally understand that when we have a cohesive material, the cohesive material is high in the water content. I mean that it will have high water content. Instead of the cohesionless soil, the water content easily free drainage. So these are the materials that we can expect what we're going to happen when we involve in construction, slope construction, for example. So there's a lot of precaution work can be done when we understand the slope material when we're dealing with, so that this can be avoid any slope failure. Okay, we go to the next slides on the failure mechanism. Okay, the slope failure mechanism here is to describe the failure types of the slope. So what we may learn from here is the types of mass movement, factors to slope failures, types of slope failure mechanism. So we go to the first one, types of mass movement. So these are two examples of the mass movement. For example, here faults, and number two is the translational slide. What is a fault actually? Falls, if you look at from the textbook or any reference, it may say or it is involved with a movement away from existing discontinuities such as joints, fissures, steeply inclined bedding planes, fault planes, and etc. So this is precipitated by the effects of water or ice pressure. So you can see here, for example, the slope failure of the mass movement fault, it is involved with a rock mass. So in the rock mass, we can have the joint beddings, we have the discontinuities. So this is the process where the mass move away from the existing discontinuities. And also discontinuities create to the fault types of the rock movement. However, for translational slides, it is one of the slides or what we call is a mass movement in the slide form. It is a movement of the mass remain essentially intact while sliding along a definite failure surface. So for slide, there are two categories. For example, translational slide and also the rotational slide. For the translational slide, images involved with a linear movement of rock blocks along bedding planes or a soil layer lying near to the sloping surface. So the such movement are normally fairly shallow and parallel to the surface. So the translational slide here couldn't see clearly on the failure plane. Later on, I will show you the translational slide compared to rotational slide. It says that here for the translational slide, it has a planar surface and it is very shallow and parallel to the surface failure. And then for the next type of mass movement is a rotational slip or rotational slides. For rotational slides, characteristically in homogeneous soft rocks or cohesive soil, so the movement taking place along a curved shear surface in such a way that slipping mass slumps down near the top of the slope and bulks up near the toe. So this is the slip failure surface, and it sees that the curved shear surface occurred, and if you compare to the rotational slip and the translational slip, also the difference on the pattern of the slip surface itself. So the rotational slip may give to you a curved shape of the slip surface. However, when you go to the previous translational slide, it is very what we call it a planar or the same line directions of the slip surface. And also for the rotational slip, it may happen in the soft rock or cohesive soil. Okay, how about the flow? Flow, you can see that it is coming together with the water. So by definition, flow here is a slipping mass internally disrupted and moved partially or wholly as a fluid. So it is consists of the fluid that coming together with a failure. This can come after we have a heavy rainy, and then we have some sort of the some kinds of landslide. Wherever slope failure happen with in fluidity conditions, that is category on the flow mass movement. And then to the next one on the factors of slope failure. Listed a few examples, for example, erosion, earthquake, rainfall, surcharge, construction activities, cut and fill slope, groundwater seepage, and geological factors. So when you look at to these around 9 factors, we almost seen that the major factors in the slope failure is the water pressure, or what we call it the pore pressure. So when you have a heavy rain, some area may result in a slope failure. However, it's not happen in everywhere lah. It depends on the how you maintain the slope and how the constructions at the early design stage and the construction stage taken place during the slope constructed. And to this one, erosion, some cases of the slope failure, erosion can come with a flow mass movement. So it is in conditions of the fluidity mass movement. And then surcharge, when you apply overloaded on the top of the slope or at the crest of the slope surface, it may trigger to the slope failure. So that's how when you doing any constructions on the hillside or hilly face, you have to bear on mind the additional load that you apply on top of the slope face or at the crest of the slope. And the next one is a rapid drawdown, and then the groundwater seepage, geological factors, for example, on the kind of rock falls, these are the bedding planes, discontinuities, and when we have the earthquake, so this discontinuity may change or may move to the original condition, original states, and create or trigger to the slope rock fall. And these are some images showing to you the slope failure, for example, erosion, earthquake, rainfall. How does it triggers to the slope failure? Okay, and then we go to the slope failure mechanism. Okay, this is example when you are doing design stage for a stable slope. We can consider slope in the stable conditions if you have the factor of safety equal to uh, equal to 1 or more than 1. If you have a factor of safety less than 1, so we can consider the slope in the stable. And then when dealing with the slope design, the most important we have to check on the strength parameters. For example, if you have a slides along pre-existing slip surface where large displacement have occurred, I mean that this slope has a history in the failure, so the residual strength parameters should be used when you are design the slope stability. For example, for undrained condition in the total stress analysis, this is the formula that we involve with the shear stress and the shear strength of the slope. And for drain, for effective stress analysis, so these are formulas involved. For example, the shear stress is equal to effective normal stress tangent effective residual friction angle. So it is important we use the appropriate parameters to design the stability of the slope. By definition, factor of safety, you can have the formula with the shear strength of the soil to the shear stress. And just now shows to you if you have a slope in the stable conditions and then coming with a few factors, for example, additional load, and then you have some earthquake and then erosions, water seepage into this soil mass, it can trigger to the slope movement. And this is what we call it as a slip surface. So this is the one kind of the rotational slip surface. Types of slope failure mechanism. There are 4 examples of slope failure mechanisms. Actually, B, C, and D in one category. So the only difference at A. So this is what we call it as a translational slide or the planar failures. Actually, you can see that the slip surface for this translational slide is a planar, and it is very shallow and also is very parallel to the surface plane. So for the category B, C, and D, this is example for base slide at B, C is a toe slide, and D is a slope slide. How to differentiate between B, C, and D? You have to check on the how does this slope failure end. For example, the slip circle at B is end at the base. It means that it stands few meter to the toe of the slope. However, for the C category, the slip circle end at the toe of the slide or end at the two of the slide circle. And for the D, so it is extend to the few meter of the two of the slope, and it is always happen which has a hard stratum underlying the slope mass. So this is how we can categorize or differentiate between A, B, C and D. And in order to more understand the differences between these categories of the slope failure mechanism, mostly on the rotational slides, you can see these are the features for B, C and D. For example, for base slides, it is also called as a base failure. The failure passing through foundations, the foundation soil somehow weaker than slope material with relatively gentle slopes. For the C, which is for toe slide, it is also called as a toe failure. Failure surface passing through toe of the slope. Material of slope is homogeneous, relatively steep slope angles. For the D, for slope slide, it is also known as a slope failure, the failure surface passing through the slope. And then for the rotational slide, let's say we assume it is happening for the homogeneous soil. So these are the features that you can use to differentiate between B base slide, toe slide, and also the slope slide. When you are doing the analysis of stability in slope for cohesive soil, it is based on the limiting plastic equilibrium. And then after defining the geometry of the slip surface, the mass of soil about to move over the surface is then considered as a free body in the equilibrium. So the forces or moment acting on the free body are evaluated, and those shear forces acting along the slip surface compared with the available shear resistance offered by the soil. And the stability of cut or build slope depends largely on changes in the pore pressure regime. So during the constructions or embankment, the pore pressure will rise, and after constructions, they will gradually fall. In cutting, however, excavation causes an initial fall in pore pressure, but as the seepage develops, they gradually rise. So you can see that what's happening in the pore water pressure changes in cutting and also the embankment. And the most critical, lowest factor of safety may be expected to occur immediately after or during construction of an embankment. After this, the soil will become stronger. In contrast, the shear strength in a cutting diminishes with the time, so does the factor of safety will be affected. So what it means here, when you are dealing with the cutting slope or the embankment slope, we have to identify what are the best strength parameters need to be used in analysis, whether it is considered as a total stress analysis or effective stress analysis. And you might see that from here, when we are dealing with the embankment, so it says that during the constructions, okay, in this embankment, during the constructions of embankment, the pore pressure will rise, and after construction, they will gradually fall. So the critical during constructions of the embankments is the at this first phase when you apply the loading of the embankment. So this part we can consider as the effective stress analysis. So we need to analyze it as a total stress analysis. It is vice versa to the cuttings. There is a difference when you compare embankment construction with the cutting constructions. So in cuttings, the pore pressure initially fall, and then they develop gradually rise. So it means that you have to determine whether you need to use the effective strength parameters or the total stress parameters. So the shear stress equal to the normal stress plus the normal stress tangent phi plus with a C. So back to the shear stress definitions and also the Moore column circle to to relate between these two phenomena in cutting and also the embankment. So to the end of this slope failure mechanism, what we can see or what we can conclude from here, it is necessary to consider both short-term end of the construction and the long-term stability. The short-term stability will be considered as completely during and immediately after constructions. Thus, we have to use the total stress method in analyzing the slope stability by using the undrained strength parameter. And you can see if we involve with a cohesive material, the phi, the internal friction angle, is equal to 0. For long-term stability problems and problems where changes in conditions, long-term dissipations of pore water pressure, it may occur long after the end of the constructions. Thus, the best parameter need to be used in the analysis is the effective stress parameter with a drain strength. And this is, we can have the C effective and also the phi effective. These are the summary of the slope failure mechanism. The next class will be involving with analyzing the slope stability. And we have to understand clearly what are differences between the short-term stability and the long-term stability. Thus can be helpful in the next class in in the slope design. So any question for this introduction topic 1? Topic 3. There's nothing much involved. I mean, it's only theoretical, just introduce to you what is the slope, what are slope types, and then how to categorize slope failure, slope mechanism, what are factors involved. So I hope that you can do your learning activity 1. So it's quite easy. It just taken from these notes, and I think that every one of you can answer this learning activity easily. All notes are given in the future. You can access notes from here. And I think that if you have no more questions, or do you have any questions before we end our class this afternoon?
Jam.
Yes?
Boleh tak saya nak copy notes ni sebab tak ada dekat island.
Boleh. Nanti saya upload. Oh, sekejap. Ada lagi tak